Welcome back to elementary statistics. In this video, we're going to be talking about box and whisker plots. But what we're really going to be talking about is trying to continue our discussion of relative position, or discussing how a particular score compares to the rest of the scores in the distribution. In a previous video, we talked about the z-score, which allows you to compare your position in one distribution to your position in another distribution. We also talked about the percentage of scores that falls in a given range as an interesting measure of how the distribution is laid out. Here we're going to take a slightly different approach. We're going to be looking at the way your score compares to the other scores within the same distribution. And there are two tools that we can use for that that are very closely related. They are the quartile and the percentile. We'll start with the percentile if I get my head out of the way. We define percentile rank as the percent of scores lower than you in the distribution. And I have both lower and you in quotes here because U is not always the correct term, right? Whichever score we care about is the one we're analyzing. And then the idea of lower can be a little bit strange depending on how the data in the distribution is ordered. But assuming that there is some sort of an order to the distribution, we're looking at the percent of scores that are lower than U. Right. Why is that popping up every time I hover my cursor? I don't know. Sorry about that. But what I'm trying to write here is that we always round this down. So for example, in a distribution with, say, 55 scores, and if I take those 55 scores and rank them from largest or from smallest to largest, you are the 41st score. That means that there are 40 scores, and then there's you, and then there's the rest, the 42nd through the 55th, which is another 14 scores. Well, your percentile rank is then going to be the number of scores below you, 40, divided by the number of scores in the distribution, 55, and then convert from a decimal to a percent by multiplying by 100%. All right, so if I pull up my calculator and I punch in 40 divided by 55 times 100, I get 72.7272, etc. The rules of rounding would tell me that I should round this up from 72.7 up to 73. But the rules for percentile rank tell me I should always round down. And so this is the 72nd percentile. More than 72% of all scores in the distribution are lower than your score. All right, percentile rank is certainly quite useful. There are a lot of places where it is worthwhile, but it turns out that in a lot of applications, it's actually too powerful, if that makes sense. You run into trouble working with percentile rank when you don't know exactly the number of scores in the distribution, or when there are so many different possibilities that trying to group things together is a little bit messy. I've seen other ways of grouping things. Instead of grouping into 100 different categories, you could group into 20 or 10 or 5, but a very common one is to group into 4 different rankings. So instead of percentile 100 ranking, we're going to do quartile 4 ranking. And to talk about quartiles, I find that it's useful to go and get a list of scores in a raw distribution. So no frequency grouping, just a giant list of scores. All right. So the specific data that you're using doesn't really matter all that much. What matters is that we have the data assembled here in increasing order. So we start at 11. Every time moving left to right and then down this page, we're getting larger and larger numbers. The lowest number is 11. The highest number is 62. There are 5 rows of data. In each row, there are 7 entries. That means that there's 35 entries in total. And I'm going to start this process off using a very similar technique to what you've seen in the past when we talked about the median. If I divide this distribution in half, this score 37 falls right in the middle. There are 17 scores lower than 37, and there are 17 scores higher than 37. All right, so the median score is 37. I'm intentionally leaving some space around where I wrote down the median score here. Actually, I'm going to run out of space here pretty quickly, so this is going to be a bit of a mess, but that's okay. All right, I'm intentionally leaving an extra line below and above that. To write down the minimum and the maximum. The minimum has now scrolled off of the screen, but we know that it was 11 and the maximum is 62, right? The smallest value and the largest value in the distribution. And again, intentionally leaving some space between those so that I can fit one row in and write in a little bit more. Because finding the median is nothing new. That's something that we've done in the past. That's something we know how to do. The quartiles want us to take that a step further. If I look just at this collection of numbers, which falls above the yellow line, there are 17 scores there. If I take the first 8 and the last 8, I can divide that bit into half and find that the median of the top half is 21. And likewise, if I look at the numbers down here below the yellow line, there are 17 scores there. 17 divided by 2 is 8.5. So I take the first 8 scores. The 9th score in this, let's try not drawing through all of the numbers. The 9th score, in this case, this 53, and then 8 more numbers that come after 53. So 53 is the median of the second half of the numbers in the distribution, the second half of the scores. And by finding these sets of values, I have divided the distribution into 4 equal parts. The lowest scores, 11, 12, 13, 14, 15, 16, 17, and 19, are scores in the first quartile. The second group, 23 through 36, are scores in the second quartile. 38 through 51 is the third quartile, and 55 through 62 is the fourth quartile. Taking these scores, taking those boundary points and writing them down, we see that given 5 numbers, we can summarize a distribution. We call this the 5-number summary. One of the few places in mathematics where I can be very happy that the naming that we use is so very on the nose. Right. Because the 5-number summary separates the distribution into quartiles, the variable that we use for the quartiles is the letter Q. And because this setup was really originally designed by computer scientists insist on always counting starting at 0. So we have Q0, Q1, Q2, Q3, and Q4, right? So if you can remember that you start counting at 0, not at 1, and you call these things Q from the lowest to the highest, right? Q because quartile, 0 through 4 because computer scientists are crazy and they think that counting should start at 0. 5-number summary because there are 5 numbers to divide the distribution into 4 regions. If you also know that a quarter, is 25%, we know that these are going to divide the distribution into some percentile ranks. Right? Q0, the minimum, is the 0th percentile. Q1 is the 24th percentile. Right? Sometimes you'll see that called the 25th percentile, but again, counting all the numbers, including Q1, 25% of the scores are below that number. Not counting Q1, generally it's 24%. Likewise, 49%, 74%, and 99%. There is no such thing as the 100th percentile of any distribution. But if you remember those as 0, 25, 50, 75, and 100, no one's going to tell you you're wrong. Things get a little bit more complicated when we try to do this with a grouped frequency table. And this is another one of those places where writing out the cumulative frequency table can be very useful. So let's take a very simple frequency distribution where I have scores of 1, 2, 3, 4, 5, 6, 7, and 8. And the relative frequencies of each, 3, 5, 7, 8, 11, 18, 12, and 9. We can use that to calculate the cumulative frequency. At this point, you should be very comfortable doing this. 3 plus 5 is 8. 8 plus 7 is 15. 15 plus 8 is 23. 23 plus 11 is 34. 34 plus 18 is 52. 52 plus 12 is 64. And 64 plus 9 is 73. Right. When we've done something like this before, we've taken 73 and divided by 2 to figure out where the median is going to be. And the median is Q2, so that's still useful. Right? 73 divided by 2 is 36.5. 36.5 is bigger than 34, but smaller than 52. So the median, Q2, is going to be 6. It's going to be one of the scores in the list of scores that are all 6. But we also want 73 divided by 4, which is 18.25. Again, 18.25 is bigger than 15, but smaller than 23. So our first quartile is somewhere in that list, from the 16th to the 23rd entry. The Q1 score is 4 in this case. To figure out the Q3 score, well, that's 3/4 of the way in. So 3/4 of 73, or just what we just calculated multiplied by 3, but that comes out at 54.75. And again, 54.75 is bigger than 52, but smaller than 64. So Q3 is one of the scores in this set of scores that are all 7. We can write down the 5-number summary. The minimum score, the lowest score in the distribution, is 1. We figured out that Q1 is 4, Q2 is 6, Q3 is 7, and then the maximum score, Q4, is 8. Right? Scores of 1, 2, 3, and 4 are in the first quartile. Scores of 4, 5, and 6 are in the second quartile. Scores of 6 and 7 are in the third quartile, and scores of 7 and 8 are in the fourth quartile. If you happen to fall on one of the numbers that is part of the 5-number summary, different schools of thought, I tend to go with the inclusive version, where the number 6 is in both the second and the third quartile. If you actually wrote this distribution out, you would see that there are a number of scores that are all 6. Some of them are in the second quartile, some of them are in the third quartile. So that, to me, makes the most sense. I'm going to steal this 5-number summary and go to some clean space to talk a little bit about how we can present this information. Now we finally get to the Box-and-Whisker plot that was the name of this video. All right, to draw a Box-and-Whisker plot, you need some space to work in. So I'm leaving some blank space here. And then below the space that you're working in, you need to draw a number line. And I'm going to make it a fairly long number line. I'm going to mark in 1, 2, 3, 4, 5, 6, 7, and 8. I want to make sure that my number line includes the minimum score and the maximum score, and might include a little bit more beyond that. It doesn't really matter. Then, in the space above the number line that I just drew, I'm going to mark down the 5-number summary. 1 is right here, so I draw a vertical line at 1, and at 4, at 6, at 7, and at 8. All right, so I draw in 5 vertical lines to represent the 5 scores in the 5-number summary. And then I draw a horizontal line through the middle connecting all of them. In order to help interpret and help read this graph, I then draw in a couple of other marks. On just the 3 scores in the middle, I draw 2 more horizontal lines going across the top and across the bottom. Sometimes you will see a box and whisker plot drawn where the lines at the top and bottom are the only ones that appear, and you don't see this line in the middle inside that box. That's entirely a stylistic choice. Whether you include that or not doesn't really change the plot at all. But here's where it gets its name. And again, very much on the nose with the naming here. A box and whisker plot consists of a box along with 2 whiskers. Whoever said mathematicians don't have a sense of humor. All right. The interpretation of a box and whisker plot comes down to where these relative sizes of each of the partitions. Remember, the space between Q0 and Q1 holds a quarter, 25% of the scores in the distribution. The space between Q3 and Q4 also holds a quarter of the scores in the distribution. So there are as many scores here in this range as there are here in this range, and here, and here. And so that is a very quick interpretation we can make. The scores in the first quartile are much more spread out. The scores in the second quartile are a little bit more closely packed. The scores in the third quartile and in the fourth quartile are very closely packed together. Thinking about some of the other things that we've talked about, there are a lot more scores low than there are high. That means that this distribution has low outliers. And if I think about the other tools I've used for describing a distribution with low outliers, I can start to make some comparisons. The median score in a distribution with low outliers is somewhere slightly to the left of the peak, which is the mode of the distribution, right? In this case, the mode I've drawn to look kind of like it's there. But then the minimum and the maximum will give you the extents of things. And the median here is 6. So we have a way of looking at the box plot and getting an idea of what the histogram or the frequency curve should look like. Or again, very simply, when you're looking at a box and whisker plot, you can look at where the data is spread out, where the data is close together, and if it's spread out on one side and close together on the other, you know there are outliers. Another thing that's commonly done with a box and whisker plot is to plot an individual score. So if your score in this distribution was 5, I would put a dot right here at 5 for you to look at. And that will tell me several things. Looking at the total range of scores, your score is somewhere in the middle. But most of the scores in the distribution are to the right, higher scores than yours. Because again, this vertical bar is the median. Half of scores are lower than it and half of scores are higher than it. You're higher than this quarter of scores, you're lower than this half of scores, and you're somewhere in the middle of this quarter of scores. So you can get a very quick understanding of how you stand compared to everyone else in the distribution just by looking at the box and whisker plot. Right. The last thing that I want to talk about in the box and whisker plot is the distance across the box. This distance is called the interquartile range, and we abbreviate that IQR, right? 3 letters, single variable. IQR is the interquartile range. We use 3 letters to write it out because it's a mouthful, but it is a single variable. And it's the distance, again, between the two endpoints of the box in the box and whisker plot. So to calculate that distance, we take the higher one, which is always Q3, minus the lower one, which is always Q1. In our particular distribution, Q3 is 7, Q1 is 4, and 7 minus 4 is 3. So the IQR of this distribution is 3. We use the interquartile range for my favorite tool for talking about and classifying outliers. All right, there are several different ways that you can talk about outliers in statistics because the idea of outliers is something that has been contentious and really analyzed by a number of people. We haven't found one option that is the right one yet. We just have a bunch of them that we throw around and we hope that some of them work out some of the time. Tukey's fences are named after the American statistician John Tukey, who published his most influential work, his study on outliers, and also the invention of the box and whisker plot in the mid-1970s. At the time I'm recording this video, the idea of the box plot and using the 5-number summary to discuss outliers is about 50 years old, which is shockingly modern by the standards of mathematics. By comparison, the study of calculus, mostly formalized by Newton and Leibniz in the 1600s, 400 or so years ago. So what we're looking at, again, is one of several tools that we can use for describing outliers. It is a very new branch of science, and there's not a lot settled. But one of the things that I do like to stress whenever I talk about outliers is that outlier does not mean mistake. Outliers occur naturally. In the rule of Tukey's fences, roughly 1 out of every 120 or so scores in a distribution should be an outlier. So if you are collecting 2,000 data points, you should have 15 or 20 outliers in your distribution. That's just how things should go. The interesting thing about outliers is trying to explain why they happen, noticing whether outliers are symmetric or clustered on one side or the other, being able to talk about what causes outliers. What do outliers mean in a distribution? Whenever you think outlier, I want you to think point of interest. Outliers are where the interesting analysis can happen in a statistical study. One of the things that outliers can help us do is understand which kinds of data are resistant to the effects of outliers. All right, so let's consider two relatively small sets of data. The first one is 15, 16, 22. Why are these so spread out? I can't write. 15, 16, 22, 23, 25, 28, 32, and 37. The second set of data, which I'll call set B, is going to be much the same, except I'm going to change two scores. Instead of 15, I now have 2. I still have 16, 22, 23, 25, 28, and 32. And instead of 37, I now have 98. Mostly the same distribution. On either extreme, I went from something that kind of fits the data to something that really doesn't fit the data. All right, I'm going to look just at a couple of relatively easy to calculate statistics on these two sets of data: the mean, the median, and the range. And I'm actually going to approach them in the other order. In data set A, the smallest value is 15, the largest value is 37. So 37 minus 15 is 22. In data set B, the smallest value is 2, the largest value is 98. So 98 minus 2 is 96. The range of data in set B is quite a bit larger than the range of data in set A. The median. Both of these distributions have 8 scores. The median is right in the middle, halfway between the 4th and 5th score, halfway between 23 and 25 is 24 in both cases. And then the mean, which we have to grab out our calculator. In data set A, I get 24.75. I'll report that as 24.8, right? One more digit than what I have in the original data. And in data set B, I get 30.75. If you want to take the time to do so, I encourage you to think about the mid-range of the two distributions, the 5-number summary of the two distributions, and the interquartile range of these two distributions. The interquartile range I'm going to at least talk about, even though I'm not going to do the calculation. The interquartile range is this space here. And in this space in the middle, the two distributions are identical. The things that are happening on the extremes are different. The things that are happening in the middle are identical. So the interquartile range will not change due to the crazy outliers. The median did not change due to the crazy outliers. The mean changed pretty drastically. The range changed very drastically. So that's some of why the median and the interquartile range can be so valuable. When you have significant outlier data, like the 98 here, which is 3 times larger than anything else in the distribution. When you have significant outlier data like that, the median and the interquartile range can be more helpful. When you have a skewed distribution where all of the data lie, or all of the outliers lie on one side and not the other, the median and the interquartile range can be incredibly useful. When you have symmetric data, when you have things that are nicely normally distributed, that's where the mean and the standard deviation really shine as tools for analyzing data. All right, let's go ahead and calculate for, just for set B. Let's go ahead and calculate what the interquartile range is. Q1 is the number halfway between 16 and 22, which is 19. Q3 is the number halfway between 28 and 32, which in this case is 30. And then so the IQR is 30 minus 19, which is 11. All right, and of course, these are the same for both of the for both of the distributions, but I'm focusing on distribution B because distribution B has some very clear extreme outliers. And I want to classify that by finding the upper fence, which is located at Q3 plus 1.5 times IQR. In this distribution, Q3 was 30, IQR was 11, and my calculator is very happy to tell me that 30 plus 1.5 times 11 is 46.5. So any score higher than 46.5 is an outlier in this distribution. The only score higher than 46.5 is 98. We can also go in the other direction. The lower fence starts at Q1 and subtracts 1.5 times the interquartile range. Our lower fence was 19. 19 minus 1.5 times 11, my calculator tells me, is 2.5. Any score smaller than 2.5 is also an outlier. And the lowest score in this distribution was 2. All right, so 2 is an outlier, although it's a relatively near outlier. 98 is an outlier, and it is a ridiculously far away outlier, which sometimes can happen. All right. So a couple of new tools at our disposal. We have the resistance statistics of the median, the 5-number summary, and the interquartile range. We can use those to talk about where the outliers are and classify them. We can draw Box-and-Whisker plots, and we can use Box-and-Whisker plots to think about how distributions fall and how distributions relate to each other, and more importantly, where you fall within a distribution. All right. I don't have any good points on discussion here, but if you've come across places where Box-and-Whisker plots, interquartile range, and outliers have been used in other courses, I'm certainly interested to hear about it. I know for anyone who has studied chemistry, you may have come across a completely different definition of outlier that chemists have really latched onto and are really fond of. If you've come across outliers in any other meanings, I'm kind of interested to hear that as well. Otherwise, I've got nothing else to talk about here. I'll wrap up the video. Thanks as always for joining me. See you next time.